All right, so when we are using triple integrals to find these volumes, we're going to need to find our bounds. It's kind of like how we did the same way when we were looking for areas. We needed to find the bounds that define the region. So this time though we have 3 bounds. So we're typically first going to find our z bounds. And so those z bounds are going to be by using surfaces and functions of x and y. And then that will be we'll have a z goes from a lower surface to an upper surface. And then what we're going to have to think through is that idea of projecting that surface onto the xy plane, which is really what we did in the past already as well, where it's kind of like I said, that idea of it's like if you were to shine a light on it, like what would the shadow look like? So what region of the xy plane is that surface being looked at over? So my solid we're going to call Q, and then that region in the xy plane is still R, and we'll need to find bounds for R the same way that we did before. So we'll kind of draw it in the xy plane and then look for either top curve, bottom curve, right curve, left curve, things like that. So the general form that this looks like though as a triple integral is, so before we took a look at double integrals, we option wrote the double integral over R. And then we did that integral with respect to area. With a triple integral now, it's going to be the triple integral over Q, so over a solid, and we'll do it with respect to volume. So a dV is really, there's those 3 components to volume. So let's take a look at an example. Let's say we want to find the volume of the sphere x squared plus y squared plus z squared equals 1. So we can already kind of picture what that sphere looks like if we draw it. It's got its center at the origin, and then it's got a radius of 1. So we see we've got something like this guy. So we can almost picture then, okay, to find bounds for z, well, really, let's go ahead and try and solve for z in this equation. So we've got z squared is going to be 1 minus x squared minus y squared. So then z is going to be, we'll do a square root, but don't forget your plus minus. So that's where our 2 curves are coming from. So we've got plus minus the square root of 1 minus x squared minus y squared, where we kind of get that idea, right? The positive square root is that upper half sphere, and the bottom square root, the negative square root, is that bottom half sphere. So z goes from the negative of that square root to the positive of that square root. So we're kind of going from the bottom hemisphere to the top hemisphere. Now, what we have to think through is, well, what region in the xy plane is all of this being looked at over? So for this one, what we can kind of picture is where those 2 surfaces meet. We can see where we are on, it actually intersects the xy plane, and that's the widest part of this particular solid. So if we look at, well, when is z 0, that's on the xy plane. So if we intersect it with the xy plane, then we would do, let z be 0, so then 0 squared, if we use this one, would be 1 minus x squared minus y squared. And we can already kind of recognize that this is a circle. We probably already had in our heads the picture that this region in R is going to be a circle. But so we've got y squared equals 1 minus x squared. So y is going to be plus or minus the square root of 1 minus x squared. If we actually draw R, you can picture where this intersects that xy plane. We've got that there's intersections everywhere at 1. And we just have a circular region. So we could have found our bounds that way as well. So we've got y goes from negative square root 1 minus x squared to positive square root 1 minus x squared. And then we can see that the numeric bounds then for x is it's going to go from -1 to +1. We go from here over to here when we're looking at those curves. So when we set up our full integral, what we're going to do then is we've got our volume. We did numeric bounds for x, so it'll go -1 to 1. And then our bounds for y were -√1 minus x squared to +√1 minus x squared. And then we've got our bounds from z is going to be negative that square root of 1 minus x squared minus y squared to +1 minus x squared minus y squared in a square root. And we're just going to integrate 1, and these would be dz, dy, dx. Little skinny there, a little hard to read maybe, but hopefully you caught the audio of what we were writing down. So at this point then we would take a look at evaluating that triple integral. So you all can practice doing that. An interesting thing that we would probably notice with this one, if we start to evaluate it, notice we're just going to integrate 1 with respect to z. And so when we integrate 1 with respect to z, we're going to get, we'll have z evaluated on the square root bound, so -1 minus x squared minus y squared, so +1 minus x squared minus y squared, and then this is still dy dx, and we've still got our bounds here. And notice what's going to end up happening is we're going to have this square root minus the negative of that square root, so we'll really end up with 2 times the square root of 1 minus x squared minus y squared, and this will be dy dx. So adding my bounds back in for my other parts. We already start to get this idea. There's a chance that we already had somewhat of this idea earlier in the problem, but notice what we see in this example at this point is we've got these expressions that they're not going to be very easy to integrate, right? If I try and do the integral with respect to y, we've got a composition where I've got a y squared underneath a square root. And I don't have my du in order to do a u substitution. But if we take a look at what those expressions look like, they're very inclined to switching to polar coordinates. So let's go ahead and make a switch to polar. Now, one thing to kind of pay attention to, that so far switching to polar coordinates technically really only works for a double integral. Polar coordinates are 2-dimensional coordinates. And so this idea that when we would try and plug them into the z formula, really z is 3-dimensional. So we will be able to do that in the future, where if you think about, right, the analogous polar coordinates up to 3 dimensions was cylindrical coordinates. So we are going to learn how to transform into other sets of coordinates. So we could have done it from the beginning of this problem, but for us, we'll do it at this step here, now that we're at a double integral. So switching to polar coordinates, notice we're going to plug in, we've got that r squared is x squared plus y squared. And then if I look at my region, I'm just going to draw an arrow from over here. If we find bounds for r and then theta, well, we can see that r goes from a radius of 0 over to 1. And then theta is going to swing that all the way, a full rotation. So we're going to go from 0 to 1 and 0 to 2 pi. So then converting this over, we're going to get the integral from 0 to 2 pi. Let's put our theta bounds on the outside. And then r goes from 0 to 1. And then we plug in, so we have 2 the square root of 1 minus really we've got a negative x squared plus y squared, so 1 minus r squared, and then don't forget your very important r dr d theta. So we add in that extra factor of r. Now at this point, what was really also helpful, not only did it simplify expressions, but now I can do the u substitution, right? I can do the 1 minus r squared and have that u of, I actually have 2r outside, so I would just need to accommodate the negative in our way there. So I'm going to let you finish up this one, but an interesting thing, if you do finish it, the final answer that we get after you do that u sub, so du would be that negative 2r dr, is we get 0 as a final answer, which seems a little funny because we're thinking about volume of a surface, or of a solid. So sometimes we would think about a positive volume, but remember when we use this setup, this type of a formula, what we're really finding is a net volume. So we are taking into account that anything that's below, anything that's negative z values are going to turn out to be quote unquote negative volume. So really it kind of makes sense with this one, right? We had just as much volume above the xy plane as we did below. So they're going to fully cancel each other out. So we'd have to think about what we would do if we genuinely wanted true volume as opposed to net volume, we would have had to make some adjustments in the beginning. So a couple things we could have recognized. We could have either split this into two problems where we could have looked at going from the xy plane to the upper half sphere. So we could have gone xy plane to upper half sphere, find that volume, find the underneath volume, so from the lower hemisphere to the xy plane separately, which would come out as a negative, and then really negate it, so take its absolute value to make it positive, and add those two together. We also, in this problem, could recognize that this is a symmetric solid, so there's just as much area on the top as there is on the bottom, or excuse me, volume on the top as the bottom. So if we did want net volume, we could double just the top area. We could have just gone from 0 to the upper hemisphere and then doubled that if we wanted genuine volume as opposed to net volume. So depends on which piece that you're looking for there in the problem. But just good things to keep in mind that as we just normally set up these integrals, if you do have negative functions, it's going to contribute to quote unquote negative volume unless you purposefully negate it to find total actual volume.